All right. So thanks everyone for having me. So my name is Chris White, and I'm actually kind of the external sort of person. So I'm coming from the Athena collaboration. It's not part of the Einstein Toolkit, but we've been doing some interesting things with radiative transfer recently. And I think this is kind of the sort of thing that the broader community might be interested in, and this might work its way into some of the parts of the code that we've been talking about so far and that we will talk about for the rest of the week. So just a quick overview, what is Athena++? This is a very general purpose astrophysics code. Its primary motivation is the study of accretion disks, the interstellar medium, star formation. It includes a bunch of different physics modules. So it's mostly MHD, but there's some relativity, there's radiation, there's self-gravity, equation of state stuff, viscosity. But I should say fundamentally, it's very much not like a relativistic code at its heart. I think of all the core developers, I'm the only one who's really interested in relativity. So it's mostly for Newtonian physics. The methods it uses the finite volume code. It has a staggered mesh constrained transport to do the magnetic fields. It has a variety of coordinate systems in it and adaptive mesh refinement, and that's what this movie is showing. Spherical coordinates, adaptive mesh refinement, you can have fun with that. So this has been out for a while. There's a general paper, there's a GRMHD paper. What I'll be talking about today is there's kind of this radiation idea that we had, which is the theory you can see written up in this 2020 paper by Shane Davis and Charles Gammy, and then the implementation came out earlier this year. And everything I'm talking about is publicly available on this GitHub. So the code is not secret, and you can take a look at the methods and all their gory detail as well. So why are we considering radiation? So the stuff I do is mostly based on accretion disks, and it's actually single black hole accretion is my main focus. And for a while, we've been doing low luminosity accreting systems, something like the galactic center, but we're trying to move more towards Eddington limited accretion systems. And when you do that, radiation becomes more important. For one, higher densities, you get radiative cooling in the disk, so it collapses to a very thin disk. The radiation to gas pressure ratio, actually in some AGN could be well over 1,000. So these are the sorts of things that's mostly radiation, and the fluid is kind of a secondary consideration. To give you some kind of context, M87 is considered kind of a low luminosity system, but it's borderline. Radiation, if you included it, would have a small effect there. Any higher accretion rate than that, you really do start to worry that you need radiation in your code. And the problem with accretion disks is fundamentally that they have optically thick and optically thin regions in the same system. So if everything were completely optically thick, kind of like the photons in a supernova, you can just account for that as an equation of state modification. You don't need to actually model the radiation directly. If everything were optically thin, you can model the effects of radiative cooling by just taking energy out of the gas. Again, you don't actually need to follow what the radiation is doing. But if you have both at the same time, you need something more sophisticated. The other issue is, in these systems, we worry a lot about disk illumination. So you have radiation coming off of a flat disk, and it's moving up into the corona or somewhere above the disk. And that point is being illuminated from multiple different directions, but not from every direction isotropically. And that's the sort of thing that's actually kind of very tricky to capture in a radiation scheme. So fundamentally, the radiative transfer equation looks like there at the top. Where I've just written the left-hand side is this kind of advective derivative along null geodesics of this Lorentz invariant quantity, specific tensity over nu cubed. All of the physics is really hidden in the definition of that D. And on the right-hand side is coupling to matter. You have an emissivity and an absorptivity and so on. That's just very standard stuff. We can write down differential equations, but the primary difficulty with radiation is that it's fundamentally collisionless. Photons or neutrinos pass right through each other. And that means effectively you have infinitely many degrees of freedom at every point in space. For comparison, in ideal MHD, you have 8 degrees of freedom at every point in space. So it's a very big difference. To be more kind of mathematical about it, if you do frequency integrated gray radiation, basically you can think of it as a function I. Intensity is just a function at every point from the sphere of possible angles into the non-negative real numbers. You're saying at every direction, there is some non-zero or non-negative amount of intensity going in that direction. If you include multi-frequency stuff, have specific intensity is a map from the sphere and frequency space into the non-negative real numbers at every point. So you have these functional degrees of freedom we're now trying to evolve instead of just a few scalars. There's secondary differential difficulties as well. In general, you have a time scale that's the cell width divided by the speed of light, which could be very short, and you have a coupling time, which is something like 1 over the opacity times the density times the speed of light. So the first one is actually only a concern to people doing Newtonian physics. If you're doing something relativistic, everything's moving at about the speed of light anyway, so that's not a worry of mine. But even in relativity, your opacities can be arbitrarily large, and so your coupling times can be arbitrarily short compared to your hydrodynamical time step. And so that is something that every radiation code has to deal with in some form or another. So I'll just go through, before I show kind of what we've been thinking of, some of the basics of what is out there. And I think the most common one is M1. So this is a long history in astrophysics going back to 1984 or so. And the idea is, let's just take this this function I, will work in the gray limit, and integrate it against these unit null vectors around the sphere of angles. And what this gets us is a radiation stress energy tensor. And then we'll just evolve the first few moments of this. So you can write down the different equations of the evolution, the time evolution of your energy density is given by a divergence of a momentum flux plus source terms. Your time evolution of the momentum in your radiation is given by the divergence of a stress plus source terms. And you can keep doing this forever and ever, and you write an infinite series of equations, but we don't want that. So the idea is, given the two things you're evolving, an energy density and a momentum flux, infer the stress and close the system of equations. So you're just evolving essentially 4 numbers. This is a very common approach in GRMHD codes, and as well as many other codes as well. And for good reason. So this is a pretty straightforward approach. It also has the benefit of kind of being correct in very important limits. In the optically thick limit, this gets the right answer. If you're free streaming far away from a single point source of radiation, it also gets the right answer. And when you're worried about radiation interacting with matter, well, matter only has 0th and 1st moments anyway, if it's collisional. So the coupling can only occur through those moments. And so, that's all that we're really evolving directly. The issue with M1 is that it kind of only understands very particular radiation fields. So I said there's 4 numbers you're evolving at every point in space or in every cell in your simulation. You can think of those degrees of freedom as 1, an overall intensity, 2 of them pick out a particular direction, and the 3rd one just scales from something like an isotropic radiation field, like I'm illustrating on the left, to a delta function pointing in one direction, all the way on the right. This would be a laser beam, for instance. And you have 1 degree of freedom to kind of scale between those. But M1 fundamentally doesn't understand multimodal intensity distributions, which is what you get when you have 2 beams of light crossing. So it just doesn't have any way of capturing that. So there's a lot of results that come out with this. We kind of want to verify with the method that we can be sure that at least in principle, we can turn up the resolution and be converging to the correct answer. There's other methods worth mentioning. There's Monte Carlo, tried and true in many areas of astrophysics, not just radiation. So the idea is basically you just launch photon packets on your grid. You can transport photons according to the null geodesic equation, that's no problem. And then they couple to the matter stochastically. So this actually very much does converge to the correct solution in a statistical sense. Some of its drawbacks, it can be slow, it can be noisy. I think this is less and less true as time goes on. People come up with good methods for optimizing this in optically thick limits. It's another issue though, it's very difficult to efficiently parallelize. If you're going to run this on 10,000 processors, you have this fundamental question, do you domain decompose in space? But then you worry about what if all your photon packets end up on one part of your domain and becomes very expensive? Or do you decompose in terms of photon packets and spread those evenly, but then every processor might need the entire grid, which won't fit into memory. So there's actually, it's tricky issues that have not been fully resolved there. Another thing I'll talk about, hybrid closure schemes kind of just take a couple of ideas from moment evolution, but with some advanced closure. So the idea is we'll evolve kind of those same M1 equations, but we won't just have some ansatz for what the second moment is that we need. Whenever we need a second moment, we could launch a few photon packets or do something locally, solve the Boltzmann equation, and kind of get a more local, more correct idea of what the second moment of the radiation is at that point. And so then you kind of try to get the best of both methods. This again is used in a number of codes that people here might be familiar with. And finally, I'll just briefly mention SN and PN methods. So here the idea is, well, for SN methods, let's just discretize that sphere of angles into n different points. That's what the n stands for. And we could, in principle, make this n a very large number and test convergence. Pn is the same thing, only instead of discretizing an angle, we kind of discretize in the Fourier transform of angles, you use spherical harmonics. So again, it's just capturing that functional degree of freedom, but trying to apply as many numbers as possible to it. You have methods are somewhere in between Sn and Pn, for instance. These also should converge. These also might be expensive. You know, if you want 1,000 numbers at every point to represent your radiation field, that's going to cost a lot. And the issue I'll talk about is kind of closest related to Sn methods, and it's also going to be a little expensive. But if I kind of put up this chart that summarizes very roughly, this is my own little analogy. On the left, these are kind of schemes you might have for evolving hydrodynamics. You have finite difference and finite element, spectral methods, particle methods, SPH methods, finite volume methods. And on the right is kind of the very rough analogy for what we do in radiation. We might just call it by a different name. So people have all different schemes and optimized for different regimes. But the question we were asking ourselves is, what's the closest to finite volume? We have a finite volume hydrodynamics code that works very well. Is there something that kind of uses the same framework and solves the radiation equations? And so that's what we did. So how do we do general relativistic radiative transfer in Athena++? We're calling it, the finite solid angle method, for lack of a better term. So start with this kind of grid, this three-dimensional grid on the right. You've discretized space into cells. In every cell, conceptually, we can put in a sphere of angles. And so we can have we can carve up that sphere into as many angles as we want. And then within every sphere, if we zoom in, there will be in every solid angle patch of that sphere, we're defining the intensity of the radiation. So if there's 100 angles in the sphere, we're tracking 100 real numbers in every cell of the simulation. I'll parameterize this with zeta hat and psi hat will be the two kind of the polar and azimuthal angles for this. They'll show up later on. And the idea then is, can we write down equations? Just as in hydro, we had fluxes of conserved quantities from one blue cell to another. Can we do the same with radiation, where radiation not only flows from one cell to another, but within a cell flows from one angular bin to an adjacent angular bin? And is there some way we can kind of write down that general radiative transfer equation in a form that kind of utilizes this discretization? The answer is yes. So now kind of going into a bit more detail, we're going to work within some orthonormal tetrad just to keep everything sane. So in every cell, we want to kind of look like special relativity. I mean, a tetrad is any set of 16 components that just that construct a basis that looks like special relativity at any point. So this fixes 10 degrees of freedom out of the 16. To keep ourselves sane, we're going to require that the local tetrad time direction is orthogonal to slices of constant time in our however we foliated space-time. So that, here's the lapse. This is what this requires. This requirement boils down to. So it fixes another 3 degrees of freedom. And that leaves you kind of 3 degrees of freedom to rotate your tetrad around in a problem-dependent way. For everything we do in Athena++, we assume at the moment, a stationary spacetime because we're doing single black hole accretion, and we may as well assume a stationary tetrad. These are not hard and fast requirements for the method, but it's just something simple, something that makes things simple to get a start. So, given a tetrad, what we're going to do is we're going to define a unit null vector in the tetrad frame. So unit because its time component has magnitude 1. And you can check this is the null vector, of course. And then by analogy, we'll define these other n components, which are not transformations of the stuff on the left, but just pre-calculated coefficients that have been named suggestively, as it'll appear later on. And they're derived from the things on the left. They're functions of space. They're functions of direction on your sphere. And they depend on these omegas. These are Ricci rotation coefficients. And so if you haven't seen those, the Ricci rotation coefficients, there's their mathematical definition in terms of the tetrad, but they really are, they're kind of the analogy of Christoffel symbols, but for showing how an orthonormal tetrad rotates as you move around through space-time. So the point is, it's a mess of equations, but as long as everything's stationary, they're pre-computed, and even if it's not, we have explicit formulas for how to compute these things. And then what do? The idea is we want to make something that looks very finite volume-ish. So here I'm showing in black is the finite volume MHD equations, right? Just mass, energy momentum, and magnetic flux conservation. So we're going to add to that on the bottom in teal a radiative transfer equation, which will look like a covariant divergence of some conserved and quantity and spatial fluxes, just like we had before, plus a momentum space divergence. So think of this in spherical coordinates, that zeta hat and psi hat and the frequency, plus some extra terms that come out because that's what the actual radiative transfer equation is equivalent to. And it's all on the right-hand side equal to emissivity minus absorptivity. And of course, whenever you add coupling to matter here, you need to account for it in the energy momentum equations. You integrate over frequency and angle, and you just add this right-hand side into that equation. But the point is, it's a mess, but we know what all these coefficients are, and it kind of looks like the same form we had before. So if I dive into that radiation equation just a bit, so if I expand all those covariant derivatives into partial derivatives, which we need to do to make the method actually implement it anyway, you can see we'll have a time derivative of something that by definition is our conserved quantity. So here it's specific intensity times geometrical factors. Beta here is a free index. You could choose it to be any time or any of your spatial indices. We generally make it time, and that means this is kind of conserving this kind of upper T, lower T version analogy to it's kind of like a part of the stress energy tensor. And anyway, this plus some sort of spatial divergence, again, with geometric factors times specific intensity, plus a derivative in frequency of more coefficients, plus derivatives in the two angular components, all equals our source terms. Again, if space-time is stationary and you choose beta to be time, this term on the right also drops out as well. So this is our differential equation. It's actually, again, it's a mess, but a solvable mess. And to make it look like finite volume, we do the same thing here that we do in hydrodynamics. You take your differential equation, you integrate it over one cell in space-time against all your coordinates, and you'll get an integral form of the equation, and we can do that as well. Here we integrate over time, all three spatial components, and all three momentum space components. And so fundamentally, the equation we solve is this 1 over delta T times a time difference of some volume averaged, frequency averaged, area, solid angle averaged conserved quantity, which involves the intensity of the radiation, plus, spatial fluxes times areas divided by volumes. That's very much what you see in hydrodynamics, plus frequency fluxes divided by frequency bid width. This is the gravitational redshift term right here, plus angular fluxes times angles divided by solid angles. So again, it's all in the same form, and it's all equal to source terms on the right-hand side. So, as the equations get more and more unwieldy to write down, they actually get kind of more and more into the form that we want so that we can plug them into a code and evolve them. And that's exactly what we do. So this is kind of the broad layout of what Athena++ or actually a lot of finite volume codes do. If you just all the tasks that take you from time t to time t plus delta t. At the start in blue, I've highlighted everything you do for hydrodynamics. You calculate fluxes, you communicate them, you apply flux divergences and source terms, then communicate your variables across MPI boundaries and so on. MHD is basically the same tasks, you just running in parallel with a few dependencies. That means you have to wait for certain things to finish in the hydro before you do the MHD, fine. And the idea is now we're adding radiation in red on the right, and it's just the same set of tasks. We're calculating fluxes and communicating them and applying flux divergences. So we're using all the same machinery that we use for hydro and MHD. It's just running this parallel sequence of tasks that have to be done. Some fun we had with this. So everything I've showed so far uses this latitude and longitude discretization, and it's easy enough to get equal solid angles on a sphere with latitude and longitude lines. But it's not really the most isotropic grid. You get these weird, very narrow solid angles near the poles and so on. So one thing we've had a lot of fun playing around with is these geodesic grids. There's many variations on this, but basically if you start with an icosahedron, you could triangulate it into as many cells as you want. project those onto the sphere. That gets you a grid of triangles. For our purposes, we take the dual grid of that. So this is, you end up with a grid of hexagons on the sphere with 12 pentagons somewhere in there. And you can do this, so you can get, for any integer n, you can get 10n squared plus 2 angles that are pretty uniformly distributed. This is a popular grid actually in the geophysics and climate modeling communities. They're always doing things on spheres. So literature has been written that kind of bounds the anisotropy of this grid, and lots of techniques have been developed using this. You can see it's a nice uniform coverage. If we want to put intensity into every cell here, we can track the radiation pretty uniformly in all different angles. So other details, as I mentioned, radiation, basically we're going to do, just as with hydro, we'll do reconstruction and flux calculations, but not just in 3 spatial dimensions, but also 2 angles and 1 frequency dimension. And on that, even on those geodesic grids I showed, there are higher order reconstruction methods. We can have high order methods as well here. Now, something this method shares in common with all radiation methods is you need some coupling to the hydro, and it'll probably need to be implicit because your coupling time can be very short. But fortunately, in relativity, that can always be a locally implicit method. The idea is you just look at the values in a cell and you can exchange energy and momentum between the radiation and the fluid. You solve some implicit equations right there. So this is built actually on kind of a precursor method in Newtonian physics that Yanfei Zhang developed. And he realized that under reasonable assumptions about the momentum transfer between the radiation and the fluid, you can actually reduce this kind of implicit solve to solving a single quartic equation, no matter how many angles or how many you're using in your radiation. So if you want 100 angles, you don't have to solve some 100 by 100 matrix problem in every cell and every time step. You just solve a quartic equation. And this actually also generalizes to general relativistic transport and fluid dynamics as well. So that's something we're doing. And like I said, our focus kind of within Athena right now is just gray transport for accretion onto a single black hole. We think there's lots of problems there that have not been fully addressed. And so there's lots of things we could do before even consider more advanced versions of this. But we will be exploring multi-frequency stuff soon. And as I mentioned before, it's all available in a branch of the public code. So it'll be merged in kind of the main branch of Athena soon enough. But if you check out the GitHub, there's actually just a specific branch that has, it's called GR radiation or something like that, and has all the details of the code. So that's kind of the background to the algorithm. And I just wanted to mention now a few tests that we run, kind of emphasizing that testing a new numerical method is very important, and I think something that's not really done quite enough or as much as it should be. So some select tests we did, and here's a very basic one, is 2 crossing beams of light in vacuum. So light is being emitted from the blue circles. The green lines indicate the maximum extent that this flashlight should have. And the idea is take 2 flashlights and angle them toward each other. The light should pass through, of course. This is just showing that happening as a function of spatial resolution, or actually, sorry, angular resolution. Spatial grid's fixed. And this is something, of course, the beams pass through each other. It's kind of a trivial test for this method. It's important to note, though, some things like M1, this doesn't work. If you take these 2 beams of light, what will happen is they will conserve energy and momentum, exactly, but they will merge and form a beam that moves perfectly horizontally to the right after they come together. So this is something we like because we think we're studying problems where we think this is kind of the sort of thing that will be happening in parts of our grid. More non-trivial tests, you can take flashlights and shine them around rotating black holes. So here's the midplane of a rapidly rotating black hole. And here's one beam that's kind of centered on the prograde photon orbit, and one on the retrograde photon orbit. And indeed, the light goes exactly where it should. There's other tests too, that I think more exotic things. So here's a whole room. This is actually, a whole room's a weird word. It's a physical device they use in labs where you fix, say, the temperature of some walls of your domain, and you ask what the radiation field or temperature is elsewhere in your domain. So here we're fixing the left and bottom boundaries. And we're saying after some time, what is the radiation field propagating off of those walls as a function of angular resolution? So from low to medium to high, and there's the exact solution. So this just shows that we're converging to the exact solution with angular resolution. And we're following, actually, there's a mock MC paper a few years ago that, they did the ones who kind of pointed us in the direction of this test. And from their paper, you can see, they show different methods. Eddington and M1, for instance, get kind of qualitatively a very weird radiation field that doesn't look like the exact solution. Whereas, their method, for instance, converges with resolution as well to the correct answer. So, that's another test that shows this. We kind of like that test that shows that we're on the right track. Of course, it's not just about transport. You want to test that you're coupling to the gas correctly. So there's standard equilibration tests. You take gas and radiation at different temperatures, and you just ask, do they approach the same temperature if you couple them, and do they approach at the correct rate? And they do here. These are these points, and they're following the analytic solution, which are the lines. That's all I'll say about that. You can also do like diffusion tests. This is something that's astrophysically relevant in a lot of cases. Imagine you have an optically thick, but mostly scattering medium. If you have a bunch of radiation in it, it should be advected with that medium, and it should diffuse out in a very predictable manner, set by the opacity. So here we start with a pulse of radiation on the left. After some time, it advects to this dashed line on the right, and it should be a little bit more diffused. And then the colored lines are as a function of angular resolution, showing that we approach, the exact solution when we put enough computational resources into it. Again, this is our motivation was we want a method that whatever the problem is, we can, at least in principle, throw resources at it and converge to the exact answer. There are radiation modified relativistic shock waves. There's a standard suite of them. I think Faris 2008 kind of enumerated a lot of these. So everyone who writes the method tends to put these in. They're annoying to actually write down what the exact answer is, but everyone has kind of the same shock tubes, and the summary is our shock tubes look like everyone else's. So we're pretty sure we're doing something right there. And the final test I want to talk about, and get on a little bit of a soapbox, is linear waves. So in my experience in writing codes, both hydro and MHD and radiation, linear wave tests are by far the best test you can ever run on a code, because it's almost impossible to have a bug, and still pass a linear wave test. For those who don't know, the idea is you choose a stationary background that will not evolve in time according to your equations. You then linearize your equations of motion, whatever they are, and then you perturb your background with a very small amplitude wave that's proportional to the eigenvector of that linear system. And then that wave should propagate at the eigenvalue. And if it's small enough, the higher order terms all drop out. And so you can then check, does my wave propagate according to the exact solution? And what's the error I get as a function of resolution? And that, if you plot this now, log error is a function of log resolution, you should get a straight line. And the slope of that line is predicted by your time integration algorithm and by your spatial reconstruction algorithm. So if you don't get the exact line you predict, something's wrong in your code. And it's very easy to make, especially in radiation, to make pretty pictures that look kind of right, but then don't pass this test. And so we spent a lot of time making sure that this test actually works. And it does actually here. So at low resolution, things are second order convergent with the way we ran the code. At high order, it becomes first order convergent because there's that locally implicit coupling is first order. So once your spatial errors are small, then your error budget is dominated by that coupling term, and that's only first order. So just as a demonstration, putting it all together, here's a standard thick torus secretion onto a spinning black hole where we just turned on the radiation as well. So I'm showing density, optical depth per gravitational length, and a magnetic to radiation pressure ratio. So as the simulation gets running, this shows the size of the box, and we're zooming in. And this just shows that, putting this all together, it all works. So we can zoom in, and then this is all done actually in Cartesian Kerr shield coordinates. So the black hole is a little bit elliptical. The ergosphere is marked in gray. And you can see, we have optical depth for gravitational length goes from 100 in the midplane to 10 to the -6 in the jet region. And it's all in the same system, but it's all handled well. And the radiation in this region, in the pink here, is actually crossing beams of radiation. It's not particularly vertically aligned, even though the average flux is vertically aligned. Just a quick preview. There's Athena K is this up and coming code. So everything I talked about was Athena++. It's in this public code. We've rewritten, or actually other people have rewritten Athena++ or parts of it with Cocos, which is the C++ library that allows you to compile for any architecture you could think of, in particular GPUs. And the reason we did this is because, as was mentioned yesterday, all the big machines are GPU based. You can't run on GPUs, you can't run on the biggest machines that are available. So here, we've only chosen a very small subset of Athena++ physics that's needed for very particular exascale problems. So in particular, radiation GRMHD on Cartesian grids. So here's just an example I ran just the other day. This is a tilted disk around a spinning black hole, density and temperature, and everything looks beautiful there. I will mention actually, Athena K did just, David Radice and company have added a Z4C solver, so it's becoming a numerical relativity code. We didn't expect that a few years ago, but here we are. Anyway, this is not public yet, but it will be released in the near future, so look forward to that. And finally, just a word on performance. Like I said, radiation, it's probably going to be expensive, and we did not choose the cheapest option. If you look at kind of typical runs on a modern CPU node, a few million cell updates per second per node, and similarly on a GPU. And that's not a really surprise. If you compare nodes to GPUs, they're made from the same silicon at the same widths. It's all going to be about the same. At low resolution, here's a breakdown of radiation in these 4 red bars. Here's hydro in blue. So radiation is 4 times as expensive as hydro. At high resolution, maybe it's 20 or 30 times as expensive, but it's not 1,000 times as expensive. We could do weak scaling tests. At least everything here is local and hyperbolic, so it weak scales very well. And there's a lot of computation per unit memory. So I don't know what's happening on Crusher, why it drops to 90%. That's a weird hardware thing. On Polaris, it goes out to 2,000 GPUs at 97%. So, that's a nice thing to show when you're applying for time at least. So putting it all together, we have this finite solid angle method for radiation, and we think this is really good for particular applications where you're worried about crossing beams of light, and you have optically thick and optically thin in the same system. The code is public, the paper is out, so if you want to take this algorithm, put it into anything in the Einstein toolkit, that'd be great too. Or if you want to ask me more questions about that, I'm happy to take questions. So I'll leave it there. Thank you.
Questions from the audience? In-person audience? Okay. Yeah.
Really nice talk, because this is also really nice work seeing sort of that you can get a weak form for these equations. So in terms of the spectral type methods that you mentioned, how do they get away with not using a weak form? Like you think find an element or something, you usually have a weak form, and then you do the integration by parts, and they, finite volume is sort of a limiting case of spectral type methods.
I don't fully understand the other method I don't work with, but I mean, my understanding though is you can construct systems where you have a very sharp discontinuity in the radiation field as a function of angle. So that's why we like the weak form. So I don't know. I mean, I imagine that just limits your convergence rate. If you're doing something spectral, it'll be, first order convergent or something. If you actually have just a sharp cutoff to your beam. How often that happens in practice though, I don't know. I mean, if you kind of have non-zero opacities in every cell, you expect your radiation field will kind of get massaged out into something smoother.
Maybe we can move on to the questions in the chat.
Actually, I don't know if there's any actual questions in the chat. Yeah.
Are there any? No. Or are there questions from the audience?
The back.
Oh, okay.
So you started off saying that at its heart, it's not a relativistic code.
Athena, yes.
But then you demonstrated that it can do a relativistic calculation, and all your equations were cast in a kind of a covariant form.
Yes.
So is it now natively kind of covariant, so you can swap out coordinate systems easily, or are there basic assumptions about what coordinates you're
I think
metric you're using?
I think now it's fair to say it is kind of natively relativistic. Athena is. The real limiting assumption that compared to say a general numerical relativity code, we really like the stationary assumption That just means there's a lot less. We don't have to evolve a metric or worry, even if it were a prescribed evolution, we don't want to do that. But other than that, I guess it is kind of, I would say it does work great for relativity. I've been using that for years, but it's just to point out like the feel of the code. I'm the only relativist involved in writing it. So most of the development is geared towards Newtonian issues and things like that. But it's great that all the physics we do kind of has that same flux conservative form of the equations, and things like constrained transport also generalize to GR just as well. So if you write things in the correct geometric way, it all kind of pops out. And so far, there's been no real issue having code that does both regimes.
You said that you don't like if the space-time is time dependent.
Yeah.
Why?
That's just because the problems we're doing are stationary, so we don't want the extra complexity if we don't need it. I think there's no fundamental reason why it can't be evolving, but it's just, as long as most of the stuff I'm doing is accretion onto a single black hole, let's keep the space-time fixed.
I guess I'm wondering, is it a psychological issue or a technical issue with the code?
It's a little,
I understand,
it's a little psychological,
but
but also it saves us on extra memory and extra calculations. And actually, as you move to GPUs, the memory constraint really becomes a problem. They're trying to fit a large, to get good scaling, you want a large, 256 cubed subgrid on every GPU. But if you're throwing in, 100 radiation angles, and then if you want to throw in, the 40 or 50 things that come from evolving space-time on top of that, like you're actually not going to be able to fit 256 cubed grids onto a single GPU these days. So if you can get whatever you can get away with as being a constant and not evolving is helpful.
Okay. So there is one more question in the chat. What is the relation between your Athena++ with C4C and GR Athena++?
Yeah, so I believe that's the same. I think that was GR Athena++ what David Radice and company put in. So they were working in Athena++, and while they were doing that, Athena K was being written. So I believe it's largely the same formulation. There's subtle differences between cell centering versus vertex centering and so on. But it's largely the same. I think most of the development though is shifted to Athena K because that's the thing that can run on GPUs. If you have a really big numerical relativity problem, you'll need that code.
I think there's another question from Eric online.
Hello, thanks for the presentation. That was really interesting. You mentioned some test cases. Is there kind of a universally agreed on test case where one could compare how good a radiation code works? I think you showed the accretion onto a black hole. Is there kind of a simple case where one could set up something similar without solving the full equations? Or would you say it's better to go back to the simple test cases that you presented in the beginning, kind of linear waves and crossing beams and so on?
Yes, I think there could be simple cases or something. I mean, in the future, it'd be nice to do kind of a code comparison or a method comparison with a standard torus accretion and different radiation methods. I think that has to be done. It's just a question of right now, there tends to be kind of every code has its method. And so when you start comparing things, it's a question of, are you really comparing method to method? Or are you really comparing just different codes? And it'll be a lot of work kind of getting the community together to make an apples to apples comparison. For example, in the GRMHD community, there was a sane comparison paper, sane torus MHD accretion problem was done 5 years ago in preparation for EHT stuff. The community still hasn't finished the MAD torus comparison. And so going on to a radiative torus comparison, I think would be still a few years off optimistically, but it should be done. That's true.
So I was thinking, for example, you could, sorry, is my time up? I'll stop then.
I think, yeah, we are a little bit over time, so maybe we move on.
Okay.
Let's thank Chris again for the very nice talk.